This is the last section of chapter 2. Remember that chapter 1, chapter 2, chapter 3 go together in your first unit, right? Test. Okay, so we're approaching that. We're getting to that. I will start chapter 3 today as well. Because we have completed 1, I will release quiz 1 today, and you should do quiz 1 before we come back on Wednesday. On Wednesday, I'll release quiz 2. That should be done. We have a whole week, right? Because we won't see you on Monday. So we may have to release 2 of them, but we'll see how far we get today. Okay? Everybody cool? All right. So section 2.4 is really going to be talking to you about the different types of graphs that are available. And many times what you have to do is you have to decide on what is considered to be a suitable graph based upon the data set. It should give you a clear picture of what the data is saying. It shouldn't be like all crowded and you really have to look to even see what is contained. As you can see, some graphs are just bad because they contain errors. Some are technically correct, but they are misleading. And one of the things I wanted you to hopefully see are some of the graphs, maybe some of you brought them today, that were very, very misleading, okay? And I see that a whole lot. Did anybody have a stat that they brought where a graph was misleading? You had one that was misleading. And what was misleading about it?
There was showing percentages, but the way that they did it, it wasn't realistic. Like 30 was like huge, and then 70 was like right next to it.
Oh, wow. So they were very misleading then, using percentages and showing percentages. Okay. Well, we're going to go different types of graphs here. This is called a scatter plot or a scatter diagram, and this is used when you're looking to see if there's a relationship between 2 variables. So one of the ones that I usually like for a scatter plot is after your first test. Many times I do a homework score or quiz score to actual test score and see if there's a correlation between those 2 things. This particular one is showing that your waist circumference compared to the arm circumference in centimeters. So, and as you can see, each dot represents a person. Comparing those 2 attributes, you can see that this pretty much is going towards a line, isn't it? Yeah. It pretty much is kind of gathered towards a line. So interesting. So we're going to learn as we continue. We are going to be able to find what's going to be called a best fit line or line of regression that would then model that data. Okay? And how strong that relationship is. This is a time series graph. And you would use a different time series graph when you have different points that are collected at different times. This particular one is over years. You see 1980 over to 2005. Okay. Time series graph. They do this on children for their growth, don't they? How many months old are you, and your height and your weight, and they look at it as the percentile of where you fit into where the population is. So that would be a graph over time. Another one is a dot plot. This is the IQ scores of a low lead group. Each dot represents 1. So if I look at 80, there's actually 3 people in the study that had an IQ of 80. If I look at 100, exactly 100, there's only one, but you can see there's two just above it and another one, and it represents each piece of data. Okay? Stem plot or stem and leaf plot, you have your first digit, or in this case, first two digits, and your last digits would be here. It's not 506. It means one particular piece of data was 50 and the other one was 56. Down here we have 141, 120, 125, 128. Okay, so you should be able to build a stem plot or a stem and leaf plot. Bar graph. A bar graph equal widths, and we show frequencies of categorical or qualitative data. Remember, we did the sums. That was really quantitative data, but we could still do it because it was discrete. And this particular one, it shows multiple in that it's comparing male and female. And I really was kind of disappointed when I saw that graph. I thought, wow, is that still true? It's multiple bar graph, meaning that the dark purplish, blue maybe, is male and the pink is female. Median income in thousands of dollars. What do you think about that graph? I think it's kind of scary to think, isn't it? Back in the year of 1950, wow. So if you kind of take a look at that, you would almost say maybe female with maybe almost 30% of what a male would make. We've made progress. We've made progress, right? Down to 210 or up to the year 210, but we certainly aren't equal yet. We certainly aren't equal yet. Why do you think that might be? Okay, good. What else comes into play? That I was thinking that a lot has been changed, but maybe not. Well, there's still, are there specific careers that are more likely female and specific careers that are more likely male? Yeah, yeah. One of the things that we try to do is especially to get females interested in STEM careers. What's STEM? Anybody know what STEM is? Science, technology, engineering, and mathematics, the STEM careers. Because, if you're a PhD in chemistry, you're probably going to make a little bit more than someone standing here teaching, right? Okay, and so we usually see those STEM careers there's more male concentration than there is female. So that's one of the things that we know we still need to do is get those interests from females in the STEM careers. So that's still probably what it's saying. Now, if they're doing equal jobs, hopefully they're getting equal pay, but I'm still not sure that's true. Right? So I thought that graph was kind of interesting. Okay, a Pareto chart is a bar graph that's just in order from highest number of frequency to the lowest number of frequency. Okay, highest frequency to the lowest number of frequency. Pie chart, everybody's seen a pie chart many times. It really should be based upon the percentage from the whole group. Percentage from the whole group. Okay? A frequency polygon and a relative frequency polygon. It's, to me, much easier to build a histogram first and then superimpose your polygon afterwards. For instance, This would be in the middle. Uses lines and segments connect to points directly above class midpoint values. This is a midpoint of a class. This is a midpoint. So you would have a bar like this, and it would be so it's easier to do the histogram or bar graph first and then put it right in the center and connect them. Same thing with relative frequency. Of course, frequency is then percents of those. An ogive graph is one that is cumulative of the frequencies. Cumulative of the frequencies. So as the example says here, if I look at this particular point, it's at 35%. So I know that there are 35 of the IQ scores are less than 89.5. Notice that it continues to go up because I'm adding on the numbers at the time. So if I look at this one, 109, and how many? Looks like about what, 70? Close to 70 are under 109.5 for their IQ. That's how you read an ogive graph. Here's some graphs that deceive. Okay? If you take a look at this graph, highway fuel consumption, miles per gallon. Well, here, if you look at this particular graph, it says, man, the Honda Civic is all over top of the Chevy and the Toyota, huh? They're like, wow, right? But when I look at it here, it's the exact same data. And then the graph is telling you the exact same thing. Doesn't look as bad, does it? Why? They pull those apart. 30, and they're counting by 1s to 36. That scale, that is compared to where they really did start at 0 and go to 40. So they've pulled it apart and exaggerated the difference. Okay? Pictographs. This is one you'll see a lot. They usually, I've seen it with like stacks of bills showing you money and funds. I've seen it with, oh gosh, so many different things. Just blocks of gold, all kinds of stuff. Well, here it gives you people, barrels, houses, etc. If you look at this and you look at the area of this compared to the area of that, tell me, how many of those little squares would fit into the big square? 4. So it's 4 times. This would indicate that something is 4 times, but many times it's really twice. But they double both the length and the width. Here they do it worse because then they're putting something that's 2-dimensional and they're forcing it to be 3-dimensional when it really should not be 3-dimensional. Okay? Here's some bad examples. What not to do if you're building graphs. These graphs both show the expected annual income by different levels of education. Notice that the bars have the same width, but it's just so busy, I have to really concentrate to really see where those are, making it difficult to understand it. Over here, they're taking something that's 2-dimensional and forcing it to be 3-dimensional. Okay? This little cube, I wonder how many of those little cubes would fit into that big cube. A lot more than 3 times, 4 times, right? Exactly. It's not that big of a difference, right? It's 4 times. Should be 4 times. So this in actuality should be 4 times or 4 of these blocks. But what they've done is they've gone 4 this way, and 4 this way. Here's an example of a good way to show this same data. Okay. Very clear, to the point, good scale. Most of the ink is used for the data itself. When we look at this being at 18.7 and this being at 74, it really is 4 times as much as it should be. Okay? So Edward Tufte has important principles about graphs. First off, if the data is real small amount of data, just give me the data in a table. Just give it to me. I can handle that. Okay? It should focus on the true nature of the data and not elements that aren't really the data. Many times they try to make them cutesy or, something representing something, and it doesn't necessarily give us a good design. Don't distort the data. Like the one that we saw for the miles per gallon, that would be a big distortion. And as he says, almost all the ink in the graph should be used for the data, not for the other design elements. Don't make it crowded. Don't make it busy. Okay?